So first of all today we're going to look at a rule which will make life a little bit easier. The first rule is what's known as the chain rule. Formally that's the definition. So u is some function of x. If you want to differentiate some function of x to a power, how you would handle that. Now of course that's not how I do it. That's how I do it. I find it much easier. So chain rule is bring down the power, lower the power, diff the inside. Think of it as anarchy. Okay? So anarchy, that's when you bring down the power. Alright? So you bring down the power, but then you want to punish them. So you want to throw them on the ground. So then you lower the power. So you bring down the power, throw down the power, and then diff the inside. Well, diff the inside's equivalent to putting the boot in. So once they're down, you give them a good kick, and then the insides go, oh, yeah, because this is true anarchy here. So bring down the power, lower the power, diff the inside, also known as anarchy. So, this is an example we had the other day. Now, of course, yes, we could just expand the whole thing out. But now, we could use this chain rule because we have a function of x to some power. So we bring down the power, 2, lower the power, it becomes 1, diff the inside. So the inside of the parentheses, if I differentiate that, I get 2. There's my answer. I don't have to worry about remembering all these silly formulas of nu to the n minus 1 times u dash. I mean, and I can tidy that and I get 4 outside of 2x plus 1, which is the same answer we got the other day. The only difference is this one's factorised. Now, this is where it has a huge advantage, because yes, okay, we could expand out 3x minus 4 to the power of 7 and then differentiate each term, but yeah, that's a lot of work. Using the chain rule, bring down the power, 7, lower the power, 6, diff the inside, 3. 7 3s are 21, and we got our answer. Heck of a lot quicker than expanding the whole thing out. Doesn't have to be a linear function, of course. This time I've got a quadratic to a power. The rule still applies. Bring down the power, 3, lower the power, 2, diff the inside. This time we get 2x when we diff the inside. So we end up with 6x, x squared minus 10 squared. Just because there's a number out the front doesn't change anything. Just like we saw before with differentiation, when we bring down that power, if there's a constant already there, we just multiply by that constant. So bring down the power, 6 5s are 30, lower the power, 5, diff the inside, negative 2, and that'll tidy up to be negative 60 times 4 minus 2x to the power of 5. So the basic idea is this, because remember, derivative is a rate of change, and rates are basically fractions. So what we're really doing is this. I think this is a nicer way of writing the chain rule. You could say, well, dy dx is the same as differentiating y with respect to some other variable. I've just called it t. So dy to t times the t dx, and if you like, the t's cancel and you get dy dx. That then allows me, remember parametrics we saw back in term 1? If we've got it in parametric form, I can still differentiate without finding the actual function itself. Because what I could do with this one is, well, I'll differentiate the x with respect to t, and I'll get 4. I'll differentiate the y with respect to t, and I'll get 4t. And so then I can say, well, hang on, I know dy dx, that would be dy to t times the t dx. So I'm going to get 4t times, well, turn the dx to t upside down, we get a quarter, and it's just our parameter t would be for that one. So I could keep it all in parametrics if I wanted to. Okay, so there's the first exercise for today. So 9 E's on using our chain rule.